Hello, can you hear me? Is everyone there? Okay, let me see. Okay, try to get set up a little bit. I was a little bit late because Zoom decided to update itself when I started a class. So I had to wait for a minute for Zoom to update itself.
Are we
I believe from reading the newspapers that they're releasing all kinds of security patches. So it's not surprising that they were updating themselves. Okay. So today we're gonna go through this little introduction to Scheme. Okay, so let's go through this little introduction to Scheme. Now let's see. I have Scheme on my computer. Try to remember where. Oh, I'm sorry. Here it is. So I have Scheme on my computer. I have two different. I installed the Dr. Racket on my computer. Oh, actually, let me for want to compare Scheme to our language 8. So I'm going to download language 8. Okay. Now here is our language 8. And this program in here is the is the REPL for language 8. So let me compile that. Okay, so I've got this REPL compiled. Okay, and then if to run the REPL, I need to oh, I'm sorry, it's not a jar file, right? Run the REPL, I just run it here. Okay. Okay, there's language 8's REPL, and want to compare it a little bit to the Racket REPL. Okay, now don't get confused. On the right is a real honest to goodness, real solid, sophisticated programming language. On the left is a baby language that's got kind of a weird little REPL into it. Okay, so this one is not anywhere near as powerful as this one, but there's a lot of overlap because our language 8 was designed to actually look a lot like Racket. So in Racket, if I add two numbers, over here, I can add two numbers. Okay, see, and fair amount of the language is going to be the same. So over here, if I want to define a function, I say define f to be lambda x. Well, but in this language, I'll put x inside parentheses, and then I want lambda x to be the squaring function, x times x. Okay. Oops, I forgot another closing parentheses. Okay. And so over here, I can make the same kind of definition. Over here, in our language, I would say there for variable f. F is a lambda, and its input is x. I don't put parentheses around the x, but then I say times x, whoops, x, x, then close the times, close the lambda, close the var, okay, right? And our interpreter, actually I can turn off, if I, maybe I should turn off that stuff for now, okay? If I set this debug here to 0 and recompile and then run it, now I won't get this debugging information, which we'll explain that in a minute. So I go back over here now, it'll make it look more like Racket. So I want variable f that is a lambda, and it takes in a parameter x, and it takes the product of x with itself. Okay, and then Oh, down here, I would say f of 5 is 25. In our language, we have to say apply f to 5, and we get back 25. Okay, so our language is a little bit different than Scheme. There's a little bit of syntactic differences in Scheme. You wrap parameters in parentheses. In our language, you don't. In our language, you say apply f to 5. In their language, you just say f of 5. Okay, now let's talk a little bit about the Racket language, what it does that our language doesn't do. Then we'll go back to compare them. The main thing that Racket does that our language doesn't do is it has a list data type built into it, which is really nice. And we'll add that list. Our language 9, the last language we're going to look at will be language 9. That'll be our language with lists. So we're going to add lists to that language. That'll be the last thing we do. So a list looks like this. You say you put a what's sometimes read as a tick mark. You do it's the right apostrophe, and then you just create a list. Okay, that's a list. Okay, that's a data structure. Okay, and it can be a list of lists, so I can have something like this. Okay, that's a list of lists of lists. So that's a list. Then in here is a list. Then here is a list of lists. So this is a list of lists of lists. So notice that means it really is a tree data structure. What I just did here was a tree. The root is 2. The root is 1. The left branch is 2. The right branch of 1 has root 3. 3 has branches 4 and 5. Then 1 has a third branch that has a root 6, and then 6 only has one tree below it, which has a tree with 6 as its root with 7 below it. So you could draw a picture of that, but that is a tree. So the list data type, one of the reasons like this language is so powerful is because though its single data type, the list, can actually represent things like trees. Another thing you can do is you can do this. This is another kind of thing. Oops. Here's going to be a list of lists. Okay. That starts looking a lot like key value pairs. It's a list of lists, but each element in the list is a key value. So with a list data structure, I can represent tables and all kinds of other things. So just by arranging my list as different kinds of lists of lists, the single list data structure can be used to implement all kinds of more powerful data structures. Just like an array can be used to implement a stack or a list or a heap. The array can actually be used to build lots of data types. Once you get used to lists, you realize that a list can be a list can be a stack, a list can be a tree, a list can be a hash table. Okay, and then since the list is the most basic data structure, since the list is the most basic data type in this language, there's functions for working with lists. Okay, so here's one of the function car of a list gives you the first item in the list. It's a bizarre name, car. Car stands for content of address register. It has to do with the way they wrote this function back in the 1950s. Okay, so it's got this bizarre name for a weird historical reason. So the car function gives you the first item in a list. Okay, so I can say car of, okay, and I get the first item in the list. And then there's another function that gives you the rest of the list. It's called cooter. Cooter stood for content of decrement register. Okay, so cooter, if you give it a list, it gives you back a list that is the original list with the first item removed. So it's in a more modern terminology, This is called, car is called the first or head of the list, and cooter is called the rest or tail of the list. Okay, so it gives you a list that is the original list with the first item removed. Car gives you the first item. Cooter gives you a list with the first item removed. Then another function is called cons. Cons stands for construct. Cons takes an item and adds it to the front of the list. So it's actually building a new list. It's called cons because it actually constructs a new list with that item at the front. It does not mutate that list. So for example, if I say define L1, no, L's a bad letter. Okay, list 1. Define list 1 to be the list 1, 2, 3, 4. Okay. Then I say cons 2 onto list 1. Okay, since, oops, this is a functional programming language. Nothing ever really mutates. Okay, so there's the list 2, 3, 1, 4, but it did not change list 1. See, it constructed a new list. That's why it's called cons. It constructed a new list that is the original list with this item at the front of it, but it's a new list. Okay, so you can't act like in data structures classes, in traditional data structures classes, you learn how to insert an item at the front of a list. Cons doesn't do that. Cons does not insert 2 at the front of this list, because if it did that, it would be mutating this list. Cons builds a new list that has 2 at the front of the list that included all these items. So now I have 2 lists. I have the original list and the second list. So for example, I could have said define list 2 to be the cons of, what was it, 2 onto list 1. Okay. List 1 hasn't changed, and list 2 is a new list. Okay. All right. So the data structures are, for the most part, immutable. When you do anything, like if I take the cooter of list 1, it returns a new list, but it did not drop. It's not a drop function. You know, it did not pop 2 off of the list list 1. It didn't pop something off list 1. List 1 is still the same. Okay, so cooter of list 1 is not a pop function. Cons on list 1 is not a push function. Okay, cons and cooter, cons doesn't push something on the list. It constructs a new list that is bigger than the list it started with. Cooter constructs a new list that's smaller than the list it started with. Cons and cooter don't push and pop. And that's real easy to get mixed up with this and think that they're like a push and a pop, like what you learn in data structures classes. In fact, you didn't learn how to write these kinds of functions in data structures classes because these functions are not mutating the list. Everything you learned in a data structures class taught you how to mutate lists. Okay, so you would learn how to insert an item at the beginning of a list. You learn how to delete an item from the front of a list. You learned how to insert an item in the middle of a list. Like here's a funny thing about this language. Here's list 1. Suppose I wanted to put the number 5 between the numbers 1 and 2. I can do that, but watch how I would have to do it. I would have to see if I can do this. I want to put 5 between the 1 and the 2. So I'm going to have to cons the car of list 1. Now, car of list 1 is the 1. I'm going to cons 1 back onto the cons of 5. What am I going to cons 5 onto? The cooter of list 1. So you get them. Okay. See, that's going to insert. Now, it's not going to insert 5 into this list. It's actually going to build a new list. But that new list, okay, I'm going to take list 1. take the cooter of it, which is 2, 3, 4. So this returns 2, 3, 4. Then I cons 5 onto 2, 3, 4. That gives me the list 5, 2, 3, 4. Then I cons the car of list 1 onto that, and I get 1, 5, 2, 3, 4. See? Notice how complicated that was. Okay. Now that would be the code for inserting this item at the second slot of the original list, but it didn't modify that list. It put something into it created a new list with that item in the middle of it. Okay. This is a funny language, because the lists are immutable. They're like in Java lists, you have a function that just says insert item X into the 5th slot of a list. There is nothing like that in this language. If you really want to insert, like I wanted to insert 5 into the second item of the list, I had to go through this process. And if you think about this process, you think from the point of view of what you learned in data structures, this is an amazingly inefficient process, though it turns out it isn't really, because what it really does, it starts with one list. As soon as you call cooter of that list, it creates a second list. So now I have 2 lists. I have list 1 and the cooter of list 1. Then I cons 5 onto that. So that's my 3rd list. Then I cons car of list 1 onto that. That's my 4th list. This command created 4 lists. Well, it started with 1 list. It created 2 temporary lists, and then it returned this 3rd list. So there were altogether 4 lists. Now, 2 of them got garbage collected because I didn't name them. So I have a reference to the answer. The 2 intermediate lists essentially got garbage collected, but they were actually constructed. Cooter constructed a list that was 2, 3, 4. It existed in memory as its own list. Cons 5 put a new number on the front of that list. So now the list 5, 2, 3, 4 was in memory. And then it cons this other thing. This language doesn't do this as inefficiently as you might imagine. The actual internal operation of the language is kind of clever. So it does this fairly efficiently, but it is kind of an odd language. Even though the fundamental data structure is a list, it's not the list as you learned it in data structures class. It is a linked list, but it's what we think of as a persistent or immutable linked list. You don't ever really mutate a list. You always construct new lists. The answer to every list function is a new list. So the 3 list functions are, and then there's another list function. The other list function is empty. So you can ask, is my list empty? Okay. So list 1 it's false that list 1 is empty. Okay. All right. Then there's also the empty list. Quote, empty set of parentheses is the empty list. So you have this notion of the empty list. Actually, let me show you something kind of interesting. This is actually not what the interpreter sees. When I type quote 1, 2, 3, what the interpreter really sees is the following. What that really was the cons of 1 on the cons of 2 of the cons of 3 on the empty list. Whoops.
You transposed some letters.
Yeah. Now let's see. So there's 1 cons, there's the other cons, there's the first con. Oh, I forgot this one too. Okay. This is an example of syntactic sugar. Okay. Quote 1, 2, 3 is actually changed by the interpreter to cons 1 onto cons 2 of cons 3 of the empty list. And that's actually what the interpreter sees. Okay, so this quote is really just a shorthand for having to type all that kind of stuff there. Okay?
So does the interpreter do that in its static analysis phase?
Probably in the parser. I don't know. That's a good question. I don't know which stage that it does that in. It might even do it in the parsing stage, or it might do it in the static analysis stage. Yeah, I don't know which stage. They have this. They expand all the syntactic sugar things. There's a bunch of things in this language that amount to what we call syntactic sugar, where what you write is not really what the interpreter sees. The interpreter sees things written out in a more basic way. It could be in the parser, but it's probably in the semantic analysis stage. That would probably be the most sensible place to put it. Okay, all right. So, but then think about this. I'm building a list, right? But how many lists did I really build? I start with the empty list. I cons 3 into it. That builds one list. Then I cons 2 onto it. That builds a second list. Then I cons 1 onto it. That creates a third list. That's my answer. The other 2 lists are garbage collected. This would seem to be really inefficient, but it turns out that the internal way of doing this is much closer to what you learned in data structures. It actually, internally, it manages to do things about as efficiently as what you learned in data structures, but you're not supposed to think of it that way. You're supposed to think of it as all lists are immutable, and every function returns a new list. Functions never actually mutate any list. Okay. Now, here's another thing that's real powerful about this language. I don't have a variable x. It's undefined, right? But I can do this. Let's see. What's in that list?
Null pointers?
No, symbols. This is a new idea. X in that list, they're symbols. They're unevaluated variables. Now, if I take away the quote, now I get an error. Okay, here's a subtle difference in this language. Okay, suppose I write car of 1, 2, 3. Now suppose I write quote car of 1, 2, 3.
Be a list of lists.
Yeah. See. This there wasn't a quote in front. So this is evaluated. The quote can actually be thought of, don't evaluate this. Just leave it as a data structure. But notice that data structure, the data in it is a program, is a line of code. This is what I was talking about, that idea the other day, that the nice thing about this language is its code and its data structures overlap. The quote tells the interpreter whether it should interpret the list or just leave it alone. So this list is not interpreted, it's just quoted. This list is interpreted. Okay. Now, when it doesn't interpret it, it just treats CAR as a symbol. So here, CAR is a symbol. Okay. But when you do it like this, CAR is evaluated. CAR evaluates to a function that does the removing of the first item of a list. Now, this quote says, don't evaluate these guys. Okay, so it says, don't evaluate them. Now, what happens if I do the following? Car, now I don't quote the 1, 2, 3. Okay, unfortunately, this is going to bomb, because what happens is you start here on the left. You have a quote, you have a left parentheses with no quote. A left parentheses with no quote means you're actually evaluating. So you evaluate car. Car gives you a function that takes the first element from a list. Now car needs to evaluate its parameter. So it looks at this and says left parentheses with no quote. So that means I'm supposed to evaluate the parameter to car. So it evaluates 1 and gets a number, but it's supposed to get a function, because that's what's supposed to be after a left paren, should be a function. And it actually complains here that expected a procedure that can be applied to arguments, but it was given 1. So 1 was looked at as supposedly a function, because it's in the right after an opening parentheses. What comes after an opening parentheses is the name of a function. And it said 1's not a function, and it complained. On the other hand, if I put the quote there, then the interpreter stops evaluating. It says, oh, it started at the left, saw as the left parentheses with no quote. So it's evaluating. It evaluates car, gets a function. The function removes the first item in a list. Goes over here and has to evaluate the argument to car. Sees quote, says, okay, car's argument is this unevaluated list of 1, 2, 3. So then you get the answer 1. Okay, so quote stops things from being evaluated, and quote isn't just for lists. So for example, see that X, it was undefined. That X is an X because I'm quoting the X and I'm telling the interpreter, don't evaluate this X. So you can quote anything. You don't have to just quote a list. So when I quote a variable like that, I'm saying that the variable is a symbol. We call it a symbol in that case. Okay, so now when I quote a list, that quotes everything inside of it automatically. Okay, so by quoting the list, everything inside of it was unevaluated. Now I could do, let's see, what happens if I do this? I don't think it's going to like this. Now, I'm not evaluating anything inside here, but I didn't evaluate the quote. So I don't think it's going to, yeah, it didn't like that. So what happened was it was given a symbol. Since I didn't quote the left parentheses, it says, okay, I'm evaluating. It got in here and says, I don't evaluate the X. So I get the symbol X. But the symbol X is not a procedure. So it expected a procedure that could be applied, but it was given the symbol X. So it didn't like that either. Okay, so it's kind of, this is where the language gets a little bit tricky. This idea of quoting or not evaluating something. You can put quotes pretty much anywhere you want. So you can, so cooter of, see if I say, like, suppose I do that. That's going to blow up on me because list 1 is a list, but I didn't evaluate it. So now it's a symbol, and you can't take the cooter of a symbol. Now, I could delay, I could tell cooter, I told scheme, don't evaluate this variable. So that variable became a symbol, but cooter expected a list. It was given it expected a list. Notice it says expected pair. Well, the lists are actually technically called pairs because a list is the first item, comma, the rest of the items. So remember we talked about the car and the cooter. So in scheme way of thinking, a list is 2 things. The first item in the list and the rest of the items in the list. That's the car and the cooter. So cooter says, I expected a list, but it calls it a pair, but it was given a symbol. Okay, so it couldn't evaluate that. Okay, all right. Now, one of the more powerful things in this language is to do recursion on lists. Okay, actually, I'm going to get out of this. This is a bare bones interpreter for the. It looks like ours over here, but it's really not the interpreter that most people want to use when they're using Racket. The better interpreter to use when you're using Racket is this other one called Dr. Racket. Dr. Racket is kind of an IDE for so here, this is a real honest to goodness bare bones REPL, just like we wrote for language 8. That's a bare bones REPL, read eval print loop. Dr. Java is more of an IDE, much more powerful with a REPL built in. Down here is the REPL. Okay, so down here I can type code like define list, list 1 to be 1, 2, 3, 4. Okay. Okay. Then what's list 1? Okay. But the thing about in Dr. Racket is if you want to be able to save your work, it would be better to go up here and say, up here, define list 1 to be 1, 2, 3, 4. And define list 2 to be, say, X, Y, Z, W. Okay, and then save this in a file. So I'll call that a script file. So I'll just say script1 dot racket. This extension that people usually use is RKT for Racket. Okay. Then I could run my script. Oh, what did I do? Oh, I forgot what? Oh, see what I did wrong? I had a syntax error. Yeah. See, when I run it, essentially compiles it. I was missing a left paren there. So now I should save my work again, click run, which compiles it, and then, all right. But now there's my definitions. So now I can go down here and say, well, what's list one? List one is 1, 2, 3, 4. What's list two? List two is 1, 2, 3, 4. So, this is much nicer. You can up here, this is called the definitions pane. You're defining code up here. It's really an editor. This is really your editor pane where you can open multiple script files, and you can have multiple ones open. For example, let me go ahead and open another one. So I'll say file, new. Okay. Oh, I didn't want a new, let's see, I just wanted a new file in here. See, what do I think? New tab, I guess, here. Yeah. So that's a new tab. Okay. So I can put a couple definitions in here. Define F to be lambda x x x. Okay. So there's a definition of F. Okay. And I'll save this as script 2. Where's okay. And then I can run that script. Now I have 2 scripts and I can run both of them. I think it now see it. So list 1. Okay, and I can f of 3 is, whoops. Oh, I can't. Let's see. Do I have to? Let's see. It's been a while since I did this. Okay, f of 3 list 1. Oh, it teach them as separate. Oh, there's a way to have them both loaded. Now I don't remember how to do that. Notice that if I switch to this tab, I only have those definitions loaded. If I switch to this tab, I only have that definition loaded. I forgot now how to have them both loaded at the same time. I actually don't remember how to do that. Okay, but you could have, so in this case, I'm working with multiple files. Okay, but the files aren't working together, they're working separate. So when I have to look up how to load them simultaneously down here. Right now, it's whichever one is open up here is when I run it, that's the one that I have, I have access to those definitions. So as a scheme programmer, I would write my code up here and then test it down here. Okay. Now, this is let's look at an example of defining a recursive function. Okay. Because one of this is a language where recursion becomes a really important part. This language has no for loops. Unlike we wrote our baby language 8 to have a while loop in it. And I put that in there because you're used to having while loops in languages. But most modern functional programming languages actually don't have while loops or for loops or repeat loops. Racket doesn't have loops. You're supposed to do iteration by recursion. So for example, a real famous example is how do you write the length? Okay. How do you write the function that computes the length of a list? Now, I think that function's already defined for us. So if I go down here, the length of 1, 2, 3 is 3. Okay. All right. So I want to define my own length function. So if I want to define my own length function, I could do something like call it my length. Okay, so I'm going to define my, because I don't want to. It's not a good idea to overlook to to define a function that has the same name as something that's already in the library. So I want to define my length. Okay, so my length takes in a parameter x. Okay, now this is not a typed language, but I'm writing a function that's going to compute the length of a list. So I'm thinking x is a list, but I don't say that in the language. Okay, now I do the following. I say if empty x, okay, if x is empty, then I want to return 0. Else, I'll return what? I'll compute the length. See, I'm going to use recursion now. I'll return the length of the cooter of x. Okay. Well, actually, I can't do quite that. No, I have to be more careful than that. If the list is empty, it has length 0. But if it's not empty, there's actually two other possibilities. It could be length 1, or it could be have length more than 1. Okay. What I really want to do now, see, I can't do this because if the x has length 1, it doesn't have a cooter. Okay. So I have to do a more if statements. Then I have to say if empty the cooter of x. No, that's not right. Yeah. Okay. If the list is empty, its length is 0. Else, if the cooter of the list is empty, then the length is 1. Okay. Else, now I get my, okay, if it wasn't length 0 or length 1, it's length more than 1. So I'm going to return the length of the cooter of x.
You should use my
plus
length.
1.
Length.
Pardon me?
Do you need to plus 1 at the end of the function?
I can,
Else return the cooter x plus 1.
oh, I'm
Yeah.
yeah.
You should put
And
that
I
down.
think we don't need the second if statement because if it's empty, if its cooter is the cooter of the list is 1, it will like automatically go to 0 finally. So the second if statement is like
well, let's see. The list could be empty, in which case it has length 0. If it's not empty, it could have length 1 or length 2 or more. Okay. If it's not empty, I have to know whether it has length 1 or if I want to use recursion. Okay.
Yeah, now, but we still can combine them together because length 1 finally we will go to cooter is length 0. It's still 1 plus 0 is 1.
Oh yeah. I'm sorry. Yeah, you're right. Because the cooter of a length of list of length 1 will be the empty list.
Yeah.
The cooter of a length of right. So I can shorten this. Yeah. So I can shorten this to be just if it's not empty, I just return
1 plus cooter length cooter
plus 1 of the length of the cooter
x.
The cooter of x.
Yeah.
You should use my length, not length, since we're trying to use our own function.
Oh yeah, that's the trouble with defining your own things, because now I would be jumping from my function to their function, and so that would be real messy.
Still.
Sorry?
It'd probably still work.
Oh yeah, it would work, but you wouldn't be debugging your program, you'd be debugging their program. Yeah, it would actually give you the right answer. Okay, all right, so now I click on run, and run will tell me if I have any syntax errors in here too. So, whoops, see, I did something wrong here. I'm probably misusing the if syntax. I think multiple expressions. Oh, I don't think you even put the word else here. Yeah, you don't even use the word else. It's just like our language. If there should be three expressions. This is the Boolean part. This is the then part. This is the else part. Okay, so it's just like our if statement. You say if, and then there should be three branches. Okay, to see, did I get the, okay, so if there's one part, there's that part.
Is there any way to make this stuff more readable?
Yes, you're not supposed to use if. I was going to show you in a minute that I'm writing this using an if, and you're actually not supposed to write it using an if.
Oh.
What did I get wrong here? There's the first expression. Okay, let's try something down here.
It looks like maybe you have too many parentheses.
Okay, if true, 3, 4. Okay, if, see, okay, if false, 3, 4. So that's the syntax. It's just if expression 1, expression 2, expression 3. Okay, if empty three, 4. So that should give me 3 because this isn't. So what? Okay, so it's just supposed to be. Here's the first expression. Here's the second expression. Plus 1.
Do we need an else here?
No, because see, the syntax is if Boolean part, true part,
yeah.
false part. Yeah, so you don't use the key, just like in our language 8, you don't use the else keyword. You use the if keyword, but no else keyword. Let's see. Bad syntax, multiple expressions after identifier in.
I think you have one too many parentheses, maybe,
But
or one too few.
It's not complaining about them. I mean, they're, see, look, okay. See, there's my length. There's the sum. That's the third part of the if. Okay. See, there's the define my length x as if empty. Huh. Okay, let's comment that out. The semicolon is a comment. Let me define it a different way. Okay. Okay. There's an expression conditional. Okay. And the conditional expression is a little bit easier to write. So what I'm going to do is my first conditional is I have a bunch of, it's essentially a bunch of if clauses. So I say cond and I say, for example, empty x. If x is empty, I'm going to return 0. Okay, that's one con branch. Then I have another con branch that says, well, if it's well, now I do now I want the default con branch. So Oh, see, how do I do that? Let's see if this compiles. Huh. Let's look at the. So here's an example using if. See, there's the conditional, there's the first part, there's the second part. Okay. What did we do wrong? What's wrong with this one up here?
I think we missed the lambda keyword.
Oh, yeah.
It treats the mylength as a a variable. Like,
well, yeah.
So
that just shows you how I spent too many years since I've worked with this. Right. Define my length. I forgot the lambda keyword.
yeah.
So it's define lambda x, and then I need another. Okay.
Parentheses.
There.
Yeah.
There. Stupid mistake. Right. Really dumb. Yeah. Forgot the keyword lambda. Define my length to be the lambda that takes in x, and then this is what it does. Okay. Then down here I can run my length. So my length of 1, 2, 3, 4, 5, 6 is. Whoop. Oh. There. There. Okay, so my length works. Okay, so there's defining my length with an if statement. Okay, now that's using recursion and if statement. Now let me call this my length 1, and I'm going to do my length 2 here. Okay, and this one needs a lambda, and then it needs okay. Now let me clean this up a little bit. This one is easier to read if I do the following. So I'm going to use a little bit of indentation. So define my length to be if empty 0, otherwise. Okay, so there by writing it in multi-lines, you can read it a little better. Define my length to be lambda x, and some people would even put this down here as like this. Okay, I'm defining my length to be a lambda that takes in x. Then the body of the lambda is an if this is empty, return 0, otherwise return the plus of 1 in my length. Okay, so there's writing my length recursively using an if. But if statements aren't really the preferred way to write this in these languages. Oh, and then this was my length 1. And this is my length 2. Okay, notice that I can write it a lot more succinctly using the cond, the conditional expression. Okay, the cond expression works like this. You have a bunch, you can have as many of these as you want where you have a Boolean and then a result. And you have Boolean result, and then at the end you have just a single expression. Okay, so the syntax for cond, we would write it as something like this. The syntax for cond is conditional followed by any number of pairs of Boolean and then expression. So you have a Boolean followed by an arbitrary expression. You have 0 or more of these, and then you have just an expression. Okay, so what conditional does is, this is a list essentially of Boolean expression, Boolean expression, Boolean expression. The first Boolean that's found to be true, you return its expression. If none of these Booleans evaluate to true, then you would return that expression. This is the else clause, or the default clause. It's essentially like multiple. It essentially becomes a very elegant way to write else ifs.
That's a switch case.
But no, it's the right way to do switches. The cond expression is really the right way to write switch statements. First of all, you can write for arbitrary Booleans there. Okay, so switch statements in a lot of languages can only let you have to put integer, you have to do cases on an integer. There's no cases here. This is just an arbitrary Boolean. And yeah, so you keep checking your cases. You do the first one, the second one, the first one's true, then you return that expression. Notice how it makes this simple function, instead of it being 1, 2, 3, 4, 5 lines, it ends up just being, I can do it in just a couple lines. Okay, so cond is the preferred way to write these functions. Very few people write scheme using if statements. You can almost always write things more elegantly using cond, and that's because almost every time you write an if statement, you almost always have else if, else if, else if anyway, so they become much easier to write when you use cond. Okay, all right. Now recursion is a real key to this. When you process lists, you process them recursively. So for example, here's another example. Suppose I want to add up all the numbers in a list. So
really quick.
Yeah.
For the cond statements, does it stop at the first one that gets executed, or will it run every one that's true?
No. It's just like nested else ifs. It stops at the first one that's true. So you have this list of expressions. So you have something like this: cond Boolean 1, expression 1, Boolean 2, expression 2, Boolean 3, expression 3, Boolean 4, expression 4, expression 5. Okay, like that. You would evaluate this Boolean. If it's true, you return E1 and you're done. If this is false, you evaluate Boolean 2. If it's true, you return E2. If this is false, and then you're done. If this is false, you evaluate B3. If B3 is true, you return E3. If B3 is false, you evaluate this. If it's true, you return this. If this one's false, you return this. It's a default case. Okay, so that's what cond looks like. It's essentially, it's as if you wrote, it's the same thing. In our way, if you think of it in terms of Java or things like that, you're really writing if B1 E2, else if B2 E1, else if B3 return E3, else if B4 return else. Okay, it's exactly that. Okay, lot less typing, but this logically would turn into this. Actually, and if this was Java, I wouldn't need the, Okay, so if B1 return E1, else if B2 return E2, else if B3 return E3, else if B4 return E4, else return B5. So you stop at the first one that's true. Okay, you go. So this one and this one are the same thing, and both of them stop when they get to the first true item. Okay. The cond expression is really elegant. Yeah, it looks a lot like case. It looks a lot like case, where these are cases, But if you think about Java's case, you have breaks and you have all kinds, you have to, there's all kinds of messy stuff. A lot of companies refuse to let their coders even use case statements, except unless they can really, really explain why they should be using it, because they're notoriously prone to little errors. The Java, C, and C+ case statements are just kind of messy. Okay, Cond is a nice compromise between case and all these nested else ifs. So I don't know why more modern languages don't use Cond. There's nothing to stop Java from having Cond. Yeah, there's nothing really functional about it. It's just a very nice way to write nested else if statements. Okay, all right. So go back. Let's do another. Write another recursive function. Suppose I want to. Oh, and let me show you one other thing. Oh, okay. Suppose I want to write the function that adds two numbers. So define add two to be lambda x, well, okay, x, y, and it's just going to return the sum of x and y. Okay, there's nothing recursive here, nothing deep here, just kind of a dumb thing. Okay, so there's a function that adds two numbers. Okay, so add 2, 3, and 4. Okay, notice that what happens if I do add 2, 3, 4, 5? Okay, yeah, it complains about arity. Okay, I didn't match arity. Okay, now notice that I used x and y, and I used x here. X here was a list. Here I'm thinking these are numbers. Schemers have kind of developed a little bit of a way of finessing this. If I think of this thing as a list, the right way to do this in Scheme is say x's. For that, oh, x is plural. X holds more than one thing. So it is x's. So then I would say, if my x's is empty, then I return the cooter of my x's. Whoops. Okay. No, so then here, this is a hint that x and y aren't compound. They're just, in this case, they're just numbers. But here, this is a hint that my x is really made up of something, x isn't just a number. It's meant to be something more than numbers. The language doesn't require you to do this, but it's kind of a real common little trick to when your variables represent lists, you give them a name that's like x's in plural. Okay, now suppose I wanted to add up two lists of numbers. Okay, notice that this added up two numbers. Let's do something a little bit trickier. Define add to list. Okay, add to list. Okay, so this would be lambda. Now it'll take x's and y's. Okay, so now I'm going to add two lists. I'm assuming that x is a list of numbers and y is a list of numbers, and I want to add them up. Okay, so what would I do? Okay, well, start with Cond. Okay, well, this is a little bit tricky because the lists may not have the same length. Okay, so what we're going to do, you have to decide what to do if the lists don't have the same length. So let's make it real easy. If the lists don't have the same length, like if you give me a list 1, 2, 3, 4, and another list that's 5, 6, I'll just add up what I can. I'll add up 1 and 5 and 2 and 6, and I'll let these go. Instead of returning an error message, I'll let those go. Okay, so I'll just add up to the overlapping part. Okay, now you can say that that's not a great idea, and there's lots of ways you could do it. If the two lists don't have the same length, you could throw an error. So you could start off by saying, well, if the lists don't have the same length, throw an error. Or you could say, okay, we'll add up as much as we can. Let's do the one where we add up as much as we can. Okay, so so now I'm going to say or. Okay, if empty x's, empty x's or empty y's. Okay. Now, actually, that's okay. But let's think about different ways to do it. If I do this, if the x's are empties or the y's are empty, I would. Oh, I have to start off with the first. Yeah, Const needs brace to say I'm starting the list. Remember the syntax for Const was. Oh, I forgot. Actually, I forgot a piece. Yeah, these guys all go in a list. So these guys actually all go in. There's a little extra pair of parentheses. It's actually not quite this syntax. There's this extra pair of parentheses that go around the Const list. Okay, so yeah. Okay, so Const, if x's are empty or y's are empty, I would return 0. Okay, there's nothing to add. Okay. Oh, and I'm still missing another parenthesis in the front. Okay. Okay, so if x's are empty or y's are empty, I return 0. Okay. Now, what if they're not? Now the trouble is I don't know which one's not empty. So if that's false, one of them is not empty. Okay. But oh, no, I'm sorry. If that's false, they're both not empty. Okay. So if one of them was empty, I just return 0 because there's nothing to add. So now they're not both empty. Okay. So I want to, they both have something in them. So I'm going to add up. So actually, I'm just going to add up the car of x's with the car of y's with the add to list. So I'm going to add 3 things. I'm going to add 1 plus 5 plus the sum of what's left of both these 2 lists. So I'll add up, like I start off by adding 1 to 5, and then I add 1 to 5 to the sum of what's left in the both lists. Okay, so add up the car of x's with the car of y's with the add to of the cooter of x's with the cooter of the y's. Okay. So that's the recursive call. There's the last add. Okay. And then I need to end the list of Const, end a Const, and a define. Oh, and then, okay. I think that's right. Okay. So now add to list of quote 1, 2, 3, 4. Oops. Okay. So, oh, you notice how this is? Notice that this is not a compiled language. What do I mean by that?
It checks your stuff at runtime.
Yeah. So see, I did a dumb thing. I forgot the question mark on empty. See, empty, and it didn't know it till it ran my program. It really is an interpreted language. There is no, this is not a, there is a compiler for Scheme, but we're not using it here. You actually can get a compiler for Scheme, but we're running an interpreter. So the interpreter parses this, builds the abstract syntax tree, and then starts walking the abstract syntax tree. It didn't find out till it walked to that part of the abstract syntax tree that I had forgotten that. Yeah, I misspelled that. Okay. What happened? I think I accidentally quit Dr. Java. That's kind of weird. I accidentally seem to have quit Dr. Java or Dr. Racket. I hope that saved my work. I wonder what key I struck.
Recover.
Yeah. Okay, so here's my version just before I put the question mark there. So I need to put a question mark there. Okay, now add to list, quote, 1, 2, 3, 4, and let's do just 1, 2. Oh, what?
Well,
I've got the parentheses. Notice that this language, when you really program in this language, it becomes a real nuisance to keep all your parentheses nice and balanced. Okay. I think I have an extra. Okay. But I didn't get the right answer. It ran, but I didn't get the right answer. Okay. So, okay.
it assumed that one of them was empty and returned 0.
Yeah, but
Which shouldn't have happened.
no. Let's see.
Flatly.
Should it be and instead of or?
Yeah, I think. Yeah, if they're both empty, if this one's empty and that one's empty, you return 0. No, wait a minute. No, wait a minute. No, if one of them is empty, you stop the recursion. You don't return 0. Okay, let's think about it again. Yeah, what happens when I do this? 1 plus 5 plus the recursion, then 2 plus 6 plus the recursion. Yeah, now one of them is empty, so I should return 0. So then 0 plus 2 plus 6 plus 1 plus 5. So if one of them is empty, I return 0. Now if one of them is empty, if either one of them is empty, I should return 0. Okay. Okay. So if one of them is empty, let's see. Let's get this in sync. Add to list of empty list and empty list. Okay, that's a test case. That should be 0. Okay, okay. Then add a not empty list to an empty list. This should still give me 0. Okay, that's a test case. Okay, this should give me 2. Okay, but I'm still getting 0. Okay, so let's think. So Hmm. There's going to be some dumb little mistake like it was before when we forgot the lambda. Anybody see it yet? What? Conditional. If one of them is empty, return 0, because you can't add up things because, you know, so one of them is an empty list, so it might as well return 0. Otherwise,
Should it be the
add up.
result plus 0?
Well,
Just return the result?
I mean here,
It should just return that one number that's there if it's unbalanced.
well, I was thinking if, you know, when it gets to unbalanced, it doesn't return to 3. I was thinking it would just return nothing. Since this one is empty, it wouldn't add 3. Now, we could add up 3 to 0 and 4 to 0. Yeah, yeah, that would be another way. If you wanted to add these two, you could add this to this to this, and then 3 to 0 and 4 to 0. So you'd be adding up everything in here with everything in here. But I was thinking that it would just stop when it got to here. So it would add up 1, 5, 2, and 6 and stop. That's what I was trying to make it do. Though it wouldn't be bad. Yeah, it wouldn't be unreasonable for it to go out through. It would then add 3 to 0 and 4 to 0. But oh, I'll have to think about that. It's going to be some dumb little mistake because, you know, it's not a hard program. Yeah, but notice that languages, recursion is trickier than writing for loops. It takes practice to write recursion, and, you know, recursion can be tough to debug too, because you don't have a loop that you can step through. You know, you're calling this function and calling this function. There is a debugger in here. I don't know if we can, it's been a long time since I used it. Let's see if we can. Okay.
Huh. You might have to add that into your actual file and then try to debug that.
Oh, I see what you mean.
Yeah. And relaunch the debugger and hit run.
Or step. Okay, so we're stepping through it now. Yeah, step. So we just, okay, step. Okay, there's the or. See, our variables are 1 and 1. Is this empty? That's going to return false. This empty? That should return false. Okay, so now, yeah, we're down here to the car of X, car of Y's. Now we make the recursive call. Okay, see, now we're recursing with the two empty lists. So now we're in the recursive call. Okay, now the cond is going to return true. Okay, so it short-circuited the OR because this returned true, so it short-circuited the OR, and now we're at the 0. Okay.
Wait, what?
Yeah, what happened to the recursion? Why didn't it go?
It didn't climb back out. It just left.
Yeah.
How does
Okay,
that work?
Yeah, I don't know. It did something dumb. Oh, I bet I know. I probably have too many. This is outside. No. Okay, we run out of time. So yeah, there's something a little dumb here. Okay. So we notice how we could step through the code and watch the recursion. Something really dumb that none of us are seeing. It's going to be some really little minor thing. But I'll put this code up on the website so you can play with these examples. And then what we really want to get at is why we want nested functions, because that's what our language 8 is. We're going to talk about recursion and lists and eventually get to where we talk about nested functions and why nested functions are useful in functional programming languages. Okay, so like I said, I'll put this code up there. I'll put these examples up on the website. You can look at them. And it's going to be one of those things that as soon as class is over with, they're going to see what the mistake is. So it's probably something really simple.
Oh,
Okay.
Kraft, before you go, have you gotten any of my emails?
Yeah, I'll try to write to you real soon. Okay.
All right.
Yeah, I
Thank
got them. Yeah, I've been so busy lately that I've had trouble having time to answer. Okay.
Hey, that's fine.
Okay. So let's see. So I'm gonna stop the sharing, and then I'll end the meeting, and I'll put the video up, and I'll put the code samples up, and we'll do some more examples of scheme on Wednesday. Okay. Goodbye.
All right. Bye.